Okay. What's law of thermodynamics? The first law of thermodynamics is based on the law of conservation of energy. A machine that can operate continuously without any expenditure on energy is called a perpetual motion machine. Early attempts to construct such machines were unsuccessful. The results of all these experiments lead to the conclusion that energy can neither be created nor destroyed, but only transformed from one form to another. Hence, the law of conservation of energy is a fundamental law of nature and is universally accepted. The first law of thermodynamics can be stated in several equivalent forms, some of which are given below. Energy can neither be created nor destroyed, but it can be converted from one form to another. Whenever one form of energy disappears, an exactly equivalent amount of another form of energy appears. For example, coal contains a large amount of internal energy. When coal is burnt, this internal energy is converted into heat energy. The heat energy is then transformed into the mechanical energy of mechanical energy of steam. Which can be used to drive our train. This example illustrates that when one form of energy disappears, an equal amount of another form of energy appears. According to Joule and Maxwell, when heat is converted into work or work is converted into heat, the quantity of work obtained is mechanically equivalent to the quantity of heat involved. The total energy of an isolated system remains constant, although energy may be transformed from one form to another. Consider an exothermic reaction. During this reaction, it is released by the system into the surrounding. Even though the system loses energy, the total energy of the system and surroundings together remains conserved. That is, the loss of energy by the system is exactly compensated by the gain of energy by the surroundings. Present view on the first law of thermodynamics in nuclear reactions, a change in energy is accompanied by a corresponding change in mass and vice versa. In such process, mass and energy are not conserved separately. In 1905, Albert Einstein proposed the mass-energy equivalence relation E equal to mc squared, where E is the energy, m is the mass, and c is the velocity of light. In view of this relationship, the first law of thermodynamics may be stated as the total mass and energy of an isolated system remains constant. Although mass may be converted into energy and energy is converted into mass. Mathematical statement of first law of thermodynamics. Let us consider a system in its initial state with internal energy E1. When the system absorbs Q amount of heat from the surrounding, then it changes to final state with internal energy E2. Initial state, internal energy E1, final state, internal energy E2, change in internal energy, delta E, E2 minus E1. The change in internal energy does not depend upon the path. When the system changes from its initial state to final state, that work done by the system is W. During this process, net gain of energy equal to Q minus W from relation first and second, delta equal to Q minus W, so Q equal to delta E plus W. In terms of infinitesimal change, equation 3 can be written as dq equal to d plus dw. If the work done is pressured, volume work done, then equation 4 can be written as d equal to dq equal to d plus pdv. Question 3, 4, and 5 are mathematical statement of first law of thermodynamics. Hence, mathematical statement of the first law of thermodynamics is that the amount of heat supplied to a system is partly utilized to increase the internal energy and remaining heat energy is utilized to do work. That is dq equal to d plus pdv. If heat energy is lost by a system, then its internal energy decreases and work is done by the system on the surrounding. Different case in the first law of thermodynamics. Case first, for isobaric process, dp equal to 0. The first law of thermodynamics is written as dq equal to d plus pdv. If it is compared to enthalpy relation, dH equal to d plus PdV. So dQp equal to ds, Qp equal to delta H. Question 6. Okay, second, for isochoric process, dV equal to 0. The first law of thermodynamics is written as dq equal to d plus PdV. So dq equal to d plus PdV delta V is 0. So dqv equal to d, that is delta E, dqv equal to delta E. Question 7. For isochoric process, total amount of heat energy supplied is utilized to increase in internal energy only, and there is no work done. Case third, for isothermal process, d equal to 0. The first law of thermodynamics written is dq equal to d plus PdV, dq equal to W, dqt equal to W. For isothermal process, total amount of energy supplied is converted into work, and there is no increase in internal energy. Case IV, for adiabatic process, dq equal to 0. The first law of thermodynamics is written as dq equal to d plus PdV. So W equal to minus d. In this case, work is done by system in the compensation of internal energy. Significance of the first law of thermodynamics. The first law of thermodynamics establishes the quantitative relationship between heat and work. It states that when a certain amount of heat energy is supplied to a system, it is converted into a definite amount of work and or change in internal energy and vice versa. This law confirms the principle of conservation of energy, according to which energy can neither be created nor destroyed, but only transformed from one form to another. As a result, the first law rules out the possibility of a perpetual motion machine of first kind. It also implies that the production of work cannot occur without a corresponding expenditure of energy in the form of heat. If Q amount of heat is supplied to a system, it may be used up partly to increase in the internal energy delta E of the system and partly to produce some mechanical work, Q equal to delta E plus W. Limitation of first law of thermodynamics. The first law of thermodynamics is only concerned with the conservation of energy. It does not explain the direction of flow of heat. For example, when a stone rolls down to the bottom, then sum of kinetic energy and potential energy remain constant in any point from top to bottom on its part. If the stone rolls up, there is also conservation of energy, but why it does not take place? The first law of thermodynamics is silent about this. The first law of thermodynamics does not explain why all chemical reactions do not go to completion. The first law of thermodynamics does not tell anything about why do spontaneous reactions are unidirectional. All natural processes are spontaneous in direction which lead to the equilibrium. The first law of thermodynamics does not tell about anything. The first law of thermodynamics does not oppose for the existence of an engine having 100% efficient or self-acting machine when conservation of energy can be imagined. In fact, such type of machines cannot obtain in actual process or can be completely converted into heat, but heat cannot be completely converted into work without leaving permanent change in the system or surroundings. This fact is not explained by the first law of thermodynamics.